This is Key Assessment 3, it's Core Concepts for Lower 6 and it's Paper 2. Hopefully you've watched the Help Me video and you've got your paper back and you're just trying to figure out, you've made some corrections and you're just trying to mark it again now. This experiment, similar to the Lipase experiment you did in the lab, and you've got essentially the substrate, which is a lipid plus an alkali plus an indicator, and this alkali makes the colour, makes it a coloured solution. Doesn't even tell you which colour it is. So this makes it a colour. So now, and then we've got the enzyme, and we heat this up to the right temperature that we want for the experiment. Add, mix them together. And that indicator then goes from colour to colourless. And we're measuring that with a colorimeter and we're waiting for it to get to 0. So that's the experiment. This type of enzyme, the little starter question, some enzymes are extracellular enzymes. This one is intracellular enzyme. So it works within cells. Intercellular would be between cells, but intra means within. We got the experiment. Identify the independent variable. The independent variable is the I. I decide what this is. I am choosing this. I for independent. And that's the different temperatures that we're running the experiment at. So the independent is temperature of the enzyme or mixture or whatever. Dependent, well, this depends on the experiment. We don't know it yet. It's the things we're measuring, so it depends on the experiment. And this is our step 5, the time taken for the absorbance to reach 0. So time for absorbance to reach 0. And write it out like it is there, don't make anything up. So often these experimental questions want the independent variable, dependent variable or controlled variables that you're thinking of. Explain why the solutions were left in the water bath for 5 minutes before combining. Well, if you get them out of the fridge, they might be 5 degrees, and it will take quite a while for them to get up to 20 degrees or 50 degrees in the lab. So you want to get them to the right temperature before you do the experiment, and then you know that you're doing the experiment at the right temperature. If you put something into a water bath, 50-degree water bath, it takes a few minutes for it to get up to that temperature, so you don't want to do the experiment straight away. So we are going to say, let's the mixtures equilibrate to the experimental temperature. The mark scheme says acclimatization. Not quite. You do expect living things to acclimatize, but if you said acclimatization, that's fine. Explain why it would be inappropriate to use a buffer solution in this experiment. Well, the thing that we are measuring as our dependent variable, this absorbance, depends on this colour change, and we're starting with an alkali. The experiment is breaking this lipid down into fatty acids and glycerol, so it makes this alkali go to acid, and that indicator will go from colour to colourless. If we use a buffer, well, the whole point of a buffer is to maintain the pH, which means this alkali to acid won't happen. It will stay the same, so we won't get a colour change. So it's just going to muck up our dependent variable. So we need to say the colour change is dependent on the pH change, and we just need to explain what's going on in this experiment. The hydrolysis of lipids produces fatty acids that lower the pH, and the buffer would maintain a single pH. That's its job. So the buffer solution would stabilise, control the pH, maintain the pH at whatever pH buffer it was. So it wouldn't allow this pH change that we want in the experiment. Right, here's the experimental results. As temperature increases, the mean time taken to reach zero decreases. Faster at first, then starts to level off. It hasn't quite leveled off. And we've got our little calculation. In the Help Me video, I tried to more or less do it for you. We're calculating a rate, which is something per unit time. So something happens per unit time. That's what a rate is. We have got 2 centimetres cubed of our substrate, and each 1 centimetre cubed would contain 0.25 grams. So we've got 1 centimetre cubed contains 0.25, that's what concentration means. Another one, because we've got 2, add them together, we've got 0.5 grams. So 2 centimetres cubed of 0.25 grams per cm cubed triacetin contains 2 times 0.25 grams equals 0.5 grams. So that's how many grams we've got, and that's the first part of our grams per second. How many seconds is this running for? Well, this is at 40 degrees C. 40 degrees C, you would hopefully put your ruler on here. I've done it very vaguely on here, but it comes across to about 18 there. I'm going to use 18. You could use 18 and a half, 19. So our calculation is, we've got 0.5 grams of triacetin is converted, is digested in 18 seconds. So if we get half a gram in 18 seconds, how much would we get in 1 second? Well, an 18th of that. So we want this to be 1 second. So it's 0.5 divided by 18. So if we're changing 18 to 1, we need to do the same to the other side as well. And then we need to just put that in our calculator. 0.5 divided by 18. So that is going to equal 0.027777, etc. Okay. And standard form. So standard form, and we've got how many decimal places or significant figures should we use? Well, everything seems to be in 2 significant figures. So I'm going to use 2 significant figures. I'm going to move our decimal place. We want a number between 1 and 10, so I'm going to move that there, and then I'm going to move it again and then 2.7 or 2.8 is going to be our how many decimals is that? Yeah, 2 point, not point, yeah, okay, 2.7. I'm just looking at the mark scheme now, what it actually wanted. It seems to want, oh no, two significant places, like we said. So that's going to be 2.8, because I'm going to round it, and then times 10 to the, times 10 to the minus 2, because I've moved that decimal place to there. That's our answer. 3 marks. Some of you have done that really quick, some of you will struggle with that, need to practice. Suggest one source of inaccuracy. So you think of controlled variables, what's difficult to control? Well, we placed these tubes in a water bath, then combined them. It doesn't say whether we kept them in the water bath. It doesn't appear to be still in the water bath. So our major problem might be the temperature changes in the experiment whilst we're running that. So temperature is not controlled during the experiment, after mixing. It could cool, these 50 might cool. And that's just 1 mark, that'll get us, but you could possibly suggest the volumes when they were measured out might not, that's a usual source of inaccuracy if you use a measuring cylinder rather than a syringe or pipette, something like that. But I'm going to go with temperature there. It was not possible to determine the optimum temperature. Explain why. So in the Help Me video, we looked at this. This was a sketch of the graph that we got above there, and we decided that at the start of the experiment it's really cold, so it's taking a long time. Well, if it got really hot again and the enzyme denatured, well, it'd take a long time again. So it takes, freezing, it would take an infinitely long amount of time. If we boiled it would take an infinitely long amount of time. So those are too high. And then in the middle somewhere we've got the optimum temperature. This graph doesn't quite level off. So the optimum temperature is probably 55, something like that. And then it would go up again. So problems, we haven't got the range of temperatures that we need to test. And also, is it 55 or would it be 54 or 56? We're only going up in 5, so that's a problem. So we could do with smaller intervals. And then it's just an explanation of that for 4 marks. So let's start off with the temperature range isn't wide enough. Temperature isn't wide enough. Our explanation for this is, well, it's still decreasing. Hasn't leveled off. The graph has not leveled off. It's still decreasing. And to get the optimum temperature, we'd be wanting it to start increasing again. Has not leveled off. Would need to see it increasing again. So we'd need to see this increase to get our optimum temperature in the middle. And we need to test temperatures above 50, so that would be what we need to do. So need to test temperatures above 50 degrees C. to see this optimum temperature. For example, maybe up to, I don't know, maybe 70 degrees C, something like that. Who knows? And then we've got our problem with, well, is it 55 or is it 56, 57, to get and narrow it down. So we need smaller increments or intervals. So need smaller increments of temperature, e.g. every 1 degree C, something like that, to maintain, to determine the accurate optimum temperature, to improve the accuracy of the optimum temperature. There we go. So you do need to practice these experimental questions. That was a good one there, 15 marks.